I guess I didn't get it on. Okay. I can see many people signing in, but just a good evening from Sydney to everyone. Morning there for India. And a very good morning also to Barton, who's joining us from UK. Let me just say something about the speakers here. So everybody from Divecha and many other from ISU are joining. Already know Adish and Anasuya. Adish has been a core part of the Future Earth Secretariat that's for South Asia. And he's also done his studies in Netherlands in sustainability science and done his master's there. And glad to be able to have him talk as one of the resource person in this science awareness series where we're focusing mostly on school students and young career researchers. Welcome, Adish. And then we do have Anasuya, who's been with also the Divecha Center for almost 5 years. She's in her fifth year of PhD. And prior to this, she was working in a sustainability or solar firm, if I'm correct. That's Anasuya. And we have Barton, who's joining us from London. And Barton has been associated with us through the Taipei Hub. So I also thank the Taipei Hub for co-organizing this with us. So Barton has obtained his degree from Taiwan and his PhD degree from University of Birmingham in UK. That's where he is now. And he's a postdoctoral research there. And prior to this, he also worked in a he's also worked in a firm in the semiconductor and solar PV industry. So we have Anasuya and Barton who's had experience in field and on ground. So it'll be good to hear from both of you. Besides that, also like to welcome, I see many participants joining it, but especially a big thank you to the teams joining from Assam, from Leh, from Shillong, and also from Namchi College. With that, let me just take everybody to the session, to the webinar. Before that, could Rianne could just display the poster so that we can just know the flow of the talks. Yes, thank you. So we'll first have Anasuya talk to all about the renewable energy and the challenges there in that sector. And it will be followed by certain questions, some pressing questions from the audience, a couple of them. Then we'll switch to Barton, where he'll be telling us about the role of wind power. And he is also associated with a lot of new science in the wind power sector. He'll be sharing that with us, followed by a few question answers. And then by Adish, she'll be talking about the initiatives and all the global concerns concerning solar cells and the importance of it. And you have Rianne here who's going to take up your questions, put that in the chat box, and look forward to a very good discussion after the three talks. So please start, Anasuya.
Hello, everybody. Good morning. Can you see my screen? Yeah, so my name is Anasuya. I am from the Divecha Center for Climate Change. I'm a PhD student, and I'm going to talk about renewable energy, its challenges, and how we can take it forward. So as we know, nowadays electricity has become integral part of our life, and its consumption is growing worldwide. Yet 770 million people do not have access to electricity. So it's going to grow up when these people also get access to electricity. And of course, we have the Sustainable Development Goals, which was created by United Nations, who defined these to attain peace and prosperity for people and planet. So some of these SDGs are very closely related to energy. To name the first one will be the SDG 7, which is affordable and clean energy. There are other SDGs also which are very closely related to energy, and they are intertwined with this SDG 7. So one is that health, which is SDG 3.9, which is connected to air pollution and health. Then comes tackling climate change. Now, why electricity sector? Why today we are talking about electricity sector? We are talking about electricity sector because energy sector alone accounts for 2/3 of global carbon dioxide emission. And then over 40% of this energy related carbon dioxide emission comes from fossil fuel burning. So this is a major issue and we need to address that. And then there will be certain benefits like you can mitigate climate change, you can reach net zero, and then of course, they will help you to attain sustainable development goals. Now, to attain this decarbonization, there are several ways in the electricity sector. So why one of them is renewable, but there are so many renewable options. Why we choose wind and solar? First point, they are mature technologies. Like there are many research already has happened on them, and there are manufacturing facilities and everywhere they are being used. And as a result of this, the price, as you can see in the plot, has come down drastically. This is a IRENA report on the cost reduction of this different sources. And as you see, there is an exponential decrease in price of solar and wind both in the last decade, starting from 2010. Now, this has enabled growth of this wind and solar worldwide, and both have seen exponential increase in their capacity starting from 2000 to 2020. This shows the green shows wind and the yellow shows solar PV capacity worldwide, how they have grown. India is also not behind. So India also has its net zero emission by 2070, the goal. Now we all talk about net zero. What is net zero? So to go to net zero, it means that you have to reduce the greenhouse gas emissions to such an extent that whatever ongoing emissions are there, that can be balanced by the removal. Now, how this removal happens? Mainly by sea, ocean, and the forest. So that means necessarily that we have to reduce this carbon dioxide emission to a very large extent. And there are several points which can help us to reduce that. The first and foremost one, which comes as a NDC, National Determined Goal of India, is 500 gigawatt of renewables by 2030. That means wind and solar are going to grow heavily in India. Where do we stand right now? So here we can see the status of India. As we can observe, India also has seen exponential growth similar to world in wind and solar both. And we are 4th largest wind installation and 4th largest solar installation today. As we get more and more renewables, our electricity grid in India is going to become renewable rich. Of course, it will be a very good step towards a decarbonization, but there are going to be certain challenges. What are they? The first one is variability. How variable is renewable? So let us look at these plots where you can see wind generation day-to-day basis in Rajasthan and South India. These are the 2 high wind potential regions of India. And you see the variability. First, we can see the seasonality. Now, what is this green part? Green part is necessarily monsoon time. So wind generates only during monsoon time, which is blue line. And in other non-monsoon month, it goes down so much that the generation is only 1/4 of that. Solar is denoted by the red line, which also sees a dip during the monsoon due to cloud cover, obviously, but the variation is not as much as wind. So this makes these sources very, very seasonal. Coming to the day-to-day basis variations, here you can see two plots from a typical day in a solar plant and in a wind plant in Karnataka. And these are minute-wise variation, the small variations. So this is minute-wise data. So you can see how variable it is minute-wise basis. And then, of course, you have these daily cycles. So this shows the real variability here. Moving on to the next challenge. The next challenge is low probability, high impact events. Now, what are they? So these are the events which are very rare to occur. But of course, when they occur, they have very high impact on the entire renewable rich grid. We'll discuss more on this later. And then we, of course, have this accuracy problems of solar prediction and wind prediction. So these three things mainly makes this renewables not dispatchable, very unlike the conventional generation where you have control over the generation in coal and hydro and all these places. However, the good thing is that we have right now technologies which can help us make it more dispatchable. So let's look at those options. So the first option is smoothing of aggregate generation. The second option is hybridization, and the third one is bulk storage. So these three I'm going to get into a little bit details. However, there are other options which you can see on the screen. So there are many more options like this. Coming to diurnal smoothing. So what is diurnal smoothing? So if you look at two places like these two red dots here, so the wind speed pattern, the daily pattern of wind speed during monsoon is very different in these two places. Suppose if you have wind turbines installed in these two locations and you are going to aggregate them, you are going to get a certain amount of smoothing. This is very different from geographical smoothing because this doesn't depend on the spatial separation of these 2 points. They can be anywhere. Only thing is the pattern has to be different. This is a novel concept which we have worked on through my PhD. And we have seen that India is a very nice example of it. If we look at India's map, where red signifies that wind peaks during the morning and blue signifies the time when wind peaks in the evening, you can see a certain pattern emerge. And we have checked year-on-year data. It remains same. So that's why we can explore this to plan our new wind plants in such a way that one of them is in red area, the other one is in blue area. And when you integrate these two, you get benefit. So this is the first part of the work. This brings us to the second part where we talk about energy drought. So we have all seen and known what is drought. That means there is no rain. But what is energy drought? When there is no generation from renewable, because these are also weather dependent sources, right? So for this, we choose two regions. So the first work was based on national scale. This one is based on regional scale. So where we focus on Rajasthan and South India, these two boxes here, where the wind as well as solar potential is very high in India. What we observe, the first observation is that when we have wind drought, that means wind no generation from Rajasthan, the first left-hand side top corner plot is for wind drought in Rajasthan. You continue to have generation in Karnataka and southern India where you see blue. That means this extended period of no generation does not occur simultaneously in all over India. There are two different regions. One region, when it gets drought, the other region does not have it. You can see the plot immediately down, and you can see that when you have Karnataka wind drought, you don't have in Rajasthan. So the same thing is true for solar as well as hybrid plants. And this makes a big opportunity to avoid this regional level droughts, because if you connect this Rajasthan region with South India with a strong grid connection, you are definitely going to avoid this region level droughts. We found another opportunity also where you can hybridize wind and solar in southern India, and you can avoid these droughts to a large extent because wind droughts are more severe compared to solar, and when you combine these two, you get a good benefit. For this study, actually, we needed a very long time series because we are talking about these extreme events which do not occur every day. So right now, historically, we have 40 years length of time series of data, historical gridded data point. So we have used a tool called Image, which is stochastic weather generator. And then we have found a very long time series preserving all the statistics of the main time series. And then we did this analysis based on that. This brings us to the last part of the work where we worked on the storage and a system which has wind, solar, and storage, a combined system, and try to look at the trade-offs. Trade-offs between what? Trade-offs between the cost and the reliability of the system in a decarbonized grid, where slowly the base load which is provided by coal is going to reduce, and you have certain amount of flexibility in it. So the study region here is not region, it is a state, which is Karnataka state, where we are located. And then why this is Karnataka? Because Karnataka has third highest installation of wind and solar in India, and it's huge. And then we keep on varying the base generation, flexibility, availability, and then we project the demand, hourly demand, and then we project the hourly weather database generation and try to develop a model and try to meet these two, balance these two. How do we balance? This is a sample for 4 different seasons. Once when you have high solar, once when you have high wind, and other 2 are low wind and low solar. And these are typical 6 consecutive days of time period in that. So the selling point here to notice is that this gray region, the gray region is the time when we can't meet the demand using all our generation, in spite of having wind, solar, and storage, all 3. So if battery is there, this pink shows the battery charging. However, in high solar months, you don't have enough actually electricity to charge your battery so much, so that you end up having certain reliability issues. Coming to the high wind, you can meet all the demand during last 3-4 days, but you end up having a lot of curtailment. So these are the main challenges here where we have to look at this problem in further details. And we did simulate a lot of situations like this. And finally, we found out in a completely decarbonized grid with 6 gigawatt of flexible generation, and if we allow certain amount of curtailment of generation from renewables, curtailment means when the renewable can generate, but you are forcibly stopping it. So that kind of situation is not good from financial perspective. But for reliability, if you can allow a certain amount of that event, then finally you will achieve 93% reliability. 100% reliability is very, very difficult to achieve, at least in Karnataka's perspective. Here are the acknowledgements, and here I summarize what I discussed earlier. The first work was on diurnal smoothing, which says that you have to aggregate generation and strategically install new wind plants so that you get this benefit of diurnal smoothing based on the pattern. The second one is about selective hybridization to avoid extreme low generation events. And the third one was about wind-solar storage trade-offs in a decarbonizing electricity system. So here is my email address. So if you have question, you please ask here. If you have question later, please reach me at this email address. Thank you.
Thank you so much, Priya.
Thank you.
So that was for everybody a very broad perspective of the renewables and the technical issues or the methods and all the tools and also the principles behind it will now be explained by Barton and also Adish. But before that, thank you, Anasuya, once again for sharing this from your own research. So it would be a very good learning experience for many who have questions along the way. At the end of the session also, we'll take up more questions. But if there are any questions, please feel free to raise your hand. And also thank you to a classroom of around 30 students who are joining from KV. Is that right? Yeah, thank you for that. They're joining through the projector, and many others who you all will be pulled in as panelists so that everybody can see you as well. So if you have questions, if any of your students have questions, please raise your hand or put in the questions in the chat box, or even if any of the other resource person have a question for Anasuya, you could also raise that here. All right, if not, then we can move over to Barton and learn more on the wind sector. Barton, over to you.
Hello, everyone. I hope you can see my screen now. Yeah, I'm Barton, the research fellow in University Exeter. I'm working on the wind power. So today I'm going to talk about how is the wind power works and how it will affect our energy system in the future. So first of all, I want to talk about what's the wind power. So there's a different definition, but I quite like this one is, well, we try to use the wind energy to generate some useful work. And I guess you probably have seen some wind turbines somewhere today, but wind power has been used in the world, in the human history for like many, many years. So the very traditional one is like you can use the green wheels. In some countries, they use the wind power to pump the water, or even you selling the belt is by the wind power. So that is many example to using wind power. But like today, the most popular usage is using like to generate electricity because that is very easy to access compared to fossil fuel. And also, like one big wind turbine can produce a lot of energy for like thousands per house. So that is the way people are using wind power. So why are we using wind power? So there's a different like things like it's renewable, ideally it never run out, and it's easy to get it because wind is pretty much everywhere in the world. And one of the key things people really like it is you don't emit any greenhouse emission during the operation time. So the first one is on the right hand side, you can see that is the resource, the wind resource in the world. So you can see that the red color means the wind speed is higher than the other region, and the yellow green one is lower. You can see in Europe or some places near Taiwan, they have a lot of wind power. India, and there's some place like on the east or south coastline, and on the south mountain there are some like wind power. So those are the places that you can harvest your wind power. And another key thing is people really care about is the carbon intensity of the electricity you generate. So this figure is like when you generate 1 kilowatt hour of electricity, how much like carbon dioxide emission you would produce in terms of the whole lifetime assessment. So you can see the like coal or natural gas or oil, they have pretty high, over like 400 or 1,000. But for the renewable energy like wind and solar, they're pretty low. Like in here, the figure is below than 50. So that is the one main reason people really think to push like renewable energy, especially wind, in the energy system. So how we extract wind power? So based on the very basic science, so here is the wind power you can thinking about is like connecting energy. So you can use a very simple equation to calculate how much energy can be carried by the wind power. But in here, the most basic parameter is like what is the density of the fluid, in here is the air, but ideally you can apply for the water if you're talking about the flow in the sea or in the river. And the second key parameter is the strip area that your wind turbine or any turbine can cover. And the last one is the speed of the fluid. So those three is the key parameter that decide how much wind power can get. But because the wind turbine have a certain efficiency, so there's one key parameter we call power coefficient. That is actually how much wind power you can convert to like electricity. So this is a little bit interesting parameter because it depends on many factors. First is what is the design of your turbine, and last parameter is the turbine tip speed ratio, and that is the speed between the wind turbine and the tip of the blade. How is the speed of that? So you can see there are different design of the wind turbine. Like this one is the vertical one, and this multiple blade one, and this a very interesting. We have a two curve. So those are different wind turbine people are using today. But the most common one you can see today for the large scale wind turbine is the either 2-blade or 3-blade wind turbine, and that is because it's easier to manufacture in the large scale and generate more power. But there's one interesting curve you can see here is this power coefficient cannot reach. The maximum of this coefficient is about like nearly 0.6. So one of the reason is you can think about if this is a device can convert all the wind power to electricity, what will happen to the wind? You probably have to stop all the wind, and if you stop all the wind, then can the wind continue flowing? And the answer is probably no. So in order to keep a continuous flow of the air, you need to allow certain air keep pass through the turbine. So that's why you can't have 100% wind turbine. So another slide I would like to introduce is what is the component within the wind turbine. So there are a couple of basic components. So first you have the rotor with a blade. The typical one is a 3-blade today. And you have everything inside the big box at the behind, we call nacelle. And in the nacelle, the first two things very important is first the gearbox is convert the low rotational speed about like 10 to 20 RPM to like thousands RPM for the generator. Then the generator will start generating electricity, and the electricity will come through the power cable to the tower in the tower. And there's another two interesting system is the first. There's a control system on the turbine that can monitor the direction and the wind speed. And later there will be a yaw system to change the angle of the blade to face the wind. For example, if the wind is blowing from the east or north, today they will change the angle. Otherwise, you will have less power generation. And another typical thing is important for the wind turbine is we call power curve. And on the right-hand side, you can see in the power curve of the wind turbine, usually they will have like 3 important wind speed. The first one is cut-in speed. It means if the wind speed is below that number, you can't generate any electricity because it's too low. And once you pass that wind speed, the power generation starts increasing. But once you reach a rated output speed, you will produce the maximum electricity power. And after even the wind speed is higher than that, the power will keep continue the same. And once the wind speed is over than cut out speed, means it's too strong and it could damage the wind turbine. The wind turbine will use the brake to stop the wind turbine and prevent further damage. So that is some people probably don't know, when the wind's too strong, they can't produce electricity. And so this one tricky thing is how we can keep the same power electricity output. The thing is there's a pitch system that can change the angle of the blade. So that can keep the load on the wind turbine the same. So there's a little bit about how the wind turbine works. So I want to introduce this. There are 2 typical wind power we can see today. One is the onshore wind power generation, the other is offshore wind power. And one of the key reasons is the wind power is really affected by the currents on the ground. So for example, if you are in a city or if you're in the forest, they even have a little bit tree there, they will make the wind speed reduce close to the ground level. So that's why there will be more and more wind turbine try to build on the sea, because there's no any other like building or things will slow down the wind. And then another thing is you can see when the turbine is higher, the wind speed will be higher. So that's why nowadays all the turbines try to get in bigger and bigger and higher and higher. So the typical one you can see for the 2.5 megawatt turbine, you can see is about 100 meter high, and in the future you probably will increase to 140 meter high. But for the offshore wind, you can be nearly 150 meters today. And if you people even talking about 200 meters. So that is how the progress of the wind power technology. But except onshore and the size, one of the things people have to think about is how to build those wind farms. So one of the biggest limitations on the onshore wind turbine is pretty big, and the part needs to be transported by the road. So you can see that's a picture. When you transport a blade, it's about 80 meters long. It's very, very difficult. A lot of the cases, you just don't have the road can access to the place you want to put a wind turbine. So next time, if you want to put the wind turbine in the mountain, you need to think about, okay, how you bring those huge things to where you want to put it. But for the offshore wind power, it's slightly different, because ideally, and if you have the way to access to the pole on the sea, then you can always have more space to build a very, very big thing. So that's why today, a lot of offshore wind turbines, they are much, much bigger than onshore, because it's easier to handle big things. But the challenge is how to install them. So this is one of the examples. They use a vessel called jackup vessel. When they go to install the wind turbine at the sea, they have the four leg will extend to on the seabed, to like making it into a like stable platform to do the installation. So that is what people are doing today. So this is the trade-off between like onshore and offshore. And there's another thing I'm going to share is you can see the size of the turbines is keep increasing, and one of the reason is the cost. The energy cost can reduce. So you can see, and in today there are some turbine can be as big as the Eiffel Tower, and in future they probably will even taller, will be over 300 meters high. So that is really, really big. So just for reference, this one building in India's called Ward 1 is like nearly 300 meters high. So in the future, some of the offshore wind turbine could be much bigger than that. So that will cause a lot of challenge, like how to go get those material, because they're really big, and how to do insulation and how to maintain that. So there will be many technical and engineering challenge. So now I want to talk about the wind turbine is so big, so what is the material to make those things? So basically you can see there are about like 5 different materials. So the first one, the body of the tower and the cover of the nacelle is usually made by steel or like iron, because that have a stronger structure can make the turbine stand in the strong wind. And another thing is you have in the generator and the transformer thing, you have a lot of like electrical materials like aluminum, copper, that is for electrical transmission. And the third one is very tricky one, is the blade, because the blade is very long and needs to be very thin and light. So today most popular materials they use composite, different kind of polymer. And the last one, and the 2 more is the rare earth materials for magnetic in the generator, and there's some concrete at the bottom. So there's some and that cause some problem. For example, the iron, steel, and the concrete create a lot of carbon emission in the world. So that could make the embedded carbon the carbon emission of wind power increase. And this is another report talking about in the future, if you're going to build a lot of wind farm, you will need a lot of mining or resource from the world. So that could cause some certain environmental impact to the world. And the last thing is another very tricky question, challenge is the composite blade is very difficult to be recycled. So in the past today, what people do is once they decommission the blade, they just bury it under the ground. That is totally not very sustainable. So if we want to use a wind turbine to decarbonize our energy system and make it more sustainable, how can we do it? So there are different technology. For example, they already have like steel making process powered by like green hydrogen. So instead of using coal, they use hydrogen and produce like CO2 in the reactor. So that is one of the innovation way people are working on it now. And another one is they have like rare earth material free wind turbine, which means they have an innovative generation system in the turbine. That can be another option. And the last one is people are working on like recyclable wind turbine blade material. So that can reduce the environmental impact of wind power. So here's my last slide. So today I talked about many things, but the key thing I want to let you know is first, wind powers will be one of the very key energy sources in the future. So you probably will see more and more in the next like 10, 20, 30 years. But as you can see, the size of turbine is getting increasing. So there will be many technical challenges. So like how you design that big, how you manufacture those big things, and how you maintain and operate those things. So those will need a lot of engineer and scientists to solve those questions. And another one is the innovation is really important because now we are using wind turbine, but they still have a lot of things need to be improved, especially to make the life cycle of the turbine being sustainable. So that is my talk today. Thank you.
Thank you, Barton, for such nice, wonderful talk and presentation. So, Rianne, do we have questions?
If I'm not mistaken, I think there was a student that raised their hands, Aditya. Should I move them up to the panelists, or if you're comfortable, you can write your message on the chat or question on the chat, we can take it up as well. I can try to bring you up to panelists as well. Hi, Aditya. I think your hand was raised. Did you have a question for the talk? Hi, Rajesh. Would you have a question for anyone in the panel?
Do we have any question? Then please type it in the chat.
It's all right as well. Maybe you can come back if you would like to type the question or something in the chat box. Maybe we can come back to discussion after maybe Adish's talk, if that's all right.
Yeah, we can come back to it at the end of the 3 talks. I would like to thank Barton again for such nice presentation, and we would like to move on to Adish. Adish, please present.
Thank you.
Hello, everyone. As you have already heard from Anusuya and Martin, they have covered a lot about how are the various solar and wind energy approaches across the world, and they've talked about how it is present in India and the future challenges that the wind and solar face within our country as well. So I don't think there will be much to talk on that. So I'll be covering more on the principal aspect of solar cells, that is as to how the solar cells operate. And this is a very, how do you say, base science, which is basic science, which helps people understand as to the mechanism of it working. But first, before that, I shall cover as to how there are different, you see the energy sources within the world, and out of which the wind power is, it has a big share. And this map shows how much of the energy production is through solar. So we have around 15% of it in Australia, as you can see. And in India, we have just 5%. And across the Asia, it's almost the same. And it's the same across Americas as well. And but there are certain countries which do make use much more of solar energy because they don't have other energy sources like solar, which is easy to use. Next, I shall go talk about how there are different components in the sunlight which are useful for the energy generation. See, here in this slide, you can see that the sunlight does not directly fall on top of the solar panel, even if you do have a solar panel, in the sense that there is some that gets onto the clouds and it becomes something known as diffuse radiation, because a lot of energy is extracted through the clouds, and then a certain amount of sunlight is absorbed by the atmosphere, and that also becomes diffuse radiation. And some that fall on top of the sea and they get reflected, which is called the albedo. And the total amount of sunlight that falls on the surface, which is recorded, is called the global horizontal irradiance. And the sunlight that directly falls on the surface, which records, or the solar panel, is called the direct normal radiation. And the sunlight which has which passes through the clouds is the diffuse solar radiation. Next, we shall cover the various types of angles, in the sense, why is it important to know this, is that if you are asked as to how much of energy from the sun is falling on top of a solar panel and how much if it is used, these are the angles that we need to consider. So for example, we have the zenith angle, which has the 90 minus the alpha, which is the altitude, which can be seen through the horizontal distance from the south or any other axis. But you see that these angles are what help us determine how much of energy is generated through solar. This is an illustration to explain as to why the solar panel is kept at an angle and not vertical or horizontal on top of the surface. They are kept at an angle because the solar radiation that falls through the atmosphere is refracted, and it comes at an angle towards the surface. And because of that, we need to keep it at an angle on top of the roof or wherever you have the solar panels. So here you can see the solar panels on top of a house, and the movement of the sun from the east to the west, and how it covers the pattern of how the sun covers its daily cycle of moving from the east to the west. This is the sun path. And next, I shall come to the actual operation of the solar cell. So before that, let me tell you that a metal does not have different layers. Even though it has layers, the layers are very close to each other. And that is the reason why the electrons are able to move very much freely, and there is no energy gap in between, in the sense that when the metal is excited through any medium, the electrons are able to move very freely, and that is why they conduct electricity much easily. Whereas in insulator, they have a band gap. So what happens is that even if you put electricity into it, because there is a difference in the surfaces of within the material, the energy is not conducted, in the sense that there is a band gap of over 3 electron volts, which comes in between. So even if you apply some energy, the band gap is not crossed, and the electrons are not able to move. That's why they become an insulator. And the semiconductor is basically a metal which is able to have a shorter band gap, and the electrons are able to cross and jump through the band gap and go to the conduction band and conduct electricity. And that's why semiconductors are used for solar cells. So now let me get to the chemistry aspect of it. So here we have a hydrogen atom, and so you can see at the center of the atom you have the proton, and its orbit you have an electron. So there are different levels of orbits around an atom, and these orbits determine as to how far away the electron is from the center. So we have 1s, 2s, 2p, 3s, 3p. So they are the different orbit levels around the center of the atom that the electrons occupy. Here, the hydrogen atom has only 1 electron, so it's in the lowest state, which is the closest to the atom center. So that's why it is quite stable, and it does not react with other elements. And whereas we have helium, which has the first orbital occupied with 2 electrons. So 1s, which is the closest orbit, has 2 electrons. And next we have carbon, which has 6 electrons. And the distribution is such that it goes to 2s and 2p. So they are orbit layers around the atom. So as you can see, these two, at 2p, you have 2 electrons which are further away, and they can react with other elements. So that's why carbon can basically fuse with other elements, and because of the electrons at the outermost orbit, which is 4 electrons. So these 4 electrons in 2s and 2p can react with other elements. Next, I'll be talking about how there is silicon. Silicon, which is used as a semiconductor, has 14 electrons. And out of these, the 4 which is at 3s and 3p, which can be seen in the diagram, are able to react with other elements. And because of it, they basically need at least 8 electrons to become stable, so that they don't react to the outside world. And since silicon does not have a stable configuration, they have 4 electrons that can react with other elements. And that is why silicon is chosen as a semiconductor to generate electricity, because they are able to give away the electrons very easily, and they can react with other elements. And you can see that the periodic table, they basically tell you how many electrons are present in the outermost orbit. So the placement of each element is such that they explain to you as to how many electrons are present in the outermost orbit of the cell. So the atom. So basically you have carbon, it has 4 electrons, and silicon has 4, and germanium has 4. So they become 4 types semiconductors. And so they can, since they have 4 electrons, they can combine with another element which has 4 electrons. And that is why you can see that the light blue here is how they react with each other. So silicon and germanium, they react together. Whereas 3, 5, so 3 plus 5 semiconductor, that means that 3 in one and 5 in another, they combine together in the outermost orbit and they become a proper semiconductor. And then you have 2, 6. So 2 and 6 together becomes 8. So that you have cadmium telluride, which is basically shown here. So it forms a stable configuration when it reacts with other metals. So you can see the green which has 2 and green which has 6. So these elements they have been marked in 2 different ways to show you as to how they combine together. Next, I'll show you that even though the lattice constant, we might think that if there is greater the distance, they may not be stable, but that is not necessarily the case. As you can see, the band gap, the energy that is required to excite the electron is shown here. So the diamond does not react at all. It's an insulator, and the energy required is in 5 or 6 electron volts, and we don't see it react to electricity at all. Whereas you have the semiconductors, which are shown here to the right, like gallium arsenide and gallium phosphorus, cadmium telluride, etc., which are basically able to conduct electricity, even though they have a large lattice constant. That is, the grouping of the electrons are larger in a large way. So then we have what is a p-type semiconductor and an n-type semiconductor. So basically, p-type is when you have elements. So silicon is doped in the sense they put element on top of silicon. So some like phosphorus, they give you extra electrons. Like the n-dope is called the n-doped element. So they give you extra electrons, and some called the p-doped. P-doping is they put an element on top of the existing element, which creates holes in the sense that they lack electrons. Even though they are fused with silicon, they will still lack electrons. And because of that, they have become p-doped semiconductor and n-doped semiconductor. So in a semiconductor, we have, so they are doped with 2 types of elements. One is an n-type and one is the p-type. So the p-type gives you holes, that is lack of electron in the outermost orbit, and n-type semiconductor, which has extra electron. So it is the positive. It is giving away the electron. And whereas you can see in the p region, they are the negative because they have holes and they lack an electron. So what happens in the junction where the 2 types of semiconductor meet, there is something called as a depletion region, wherein the electrons and holes recombine, and there is a depletion of charge. There is no charge, and it generates an electric field. So here you can see there is something known as the Fermi level. So the highest level that an electron can occupy is called the Fermi level. So you need to make the electrons cross over so that the electricity is generated. So in the p-type and the n-type, they have different energy Fermi levels, and because of which there is you need to provide some energy for them to get excited enough to be able to cross the band gap. So in p-n junction of the solar cells, there are 3 essential steps that are required for the operation of the cell. One is the electron hole pair recombination, then the separation of the electron and hole at the junction, so where the wires are connected to the semiconductor, and then the collection of electrons at holes at the terminus, wherein the electrons start moving towards the holes. Electrons start moving to the holes. So here, as you can see, the light falls on top of the semiconductor. It charges the semiconductor, so which makes the electrons get excited enough to go to the next state. And that in turn gives you a current. And here you can see in a better way how the N-type has the electrons that move to the P-type, and the P-type have holes that move towards the N-type when they are connected together. And they cross over the depletion region because of the electric field generated. And depletion region is the gap between the junction, so wherein they have the positive and the negative charges. And because of which you have electricity generation that happens. That is, the light falls on top of the semiconductor, the electron gets excited, and they move towards each other through the depletion region, and they give you electricity. And this can be seen here as to how they you have another description of how they move through the solar cells. So each solar cells produces almost 5 volts, and there are a series of solar cells that are connected together, and they together give you energy in 150 watts or greater. And these are the different types of photovoltaic panels that you can see. They are monocrystalline, polycrystalline, hybrid, all black. There are different type of solar cells which generate electricity. And there are certain applications for solar cells as well, which might not be known to people. For example, in the university where I studied my master's, we have the university working on making solar powered cars. And they have already launched a car. With the help of the university, they have already launched a car called the Lightyear 1. You can search for it, Lightyear 1. And it has a range of almost 720 kilometers. And you can charge every night up to 400 kilometers. It can give you 400 kilometers if you charge it one night. And it's a very nice car, and you should check it out. It's similar to Tesla, but it is powered on solar cells. And the other major application of solar is definitely the building sector, wherein you have panels integrated on top of the buildings, like the rooftop type, the balcony type, or curtain wall type. So basically, they integrate it into the building so that they help you generate electricity for a household needs instead of relying on the grid. And there are many different components of a solar cell when it is connected to a home or a building. So basically, when you have kept it outside, you have a charge controller, a battery, and then you have an inverter. And after which you get the electrical appliances, which basically use the electricity. So what are these different types of components? I'll be explaining in a bit more detail. So the before that, let's say that we want to know why there is why people have not gone on to use solar cells so much in everyday life. The major reason is that there is very high temperature, which causes a low performance in solar cell, because the temperature is not dependent on how much it is the metal can heat. It's based on how much sunlight falls on top of it. And then there is dust collection over the panels when it is not maintained. Then even if there is just a tree next to the solar panel, it might not charge as well. And then there is also the problem of having to orient the solar cell towards a particular direction so that it gets direct sunlight. And then also, of course, there's soiling by birds. And next, I'll come to the different components of this system which we are having at home. So we have to choose a battery. And to choose a battery, we have to look at the amps and the volts, which gives us the watts. Sorry. And you'll need to know how much energy or loads are operating over the system to choose a battery. So in the sense that how much of energy is going to get generated from the solar cell has to be known before we get a battery for it. And the battery has something known as a depth of discharge, in the sense that you can have 1,500 cycles of energy discharge at 80% depth of discharge. In the sense, the battery can help you give you energy up to 80% when there's 1,500 cycles of it which has been used. And there are 3,000 cycles at 50% depth of discharge and 5,000 cycles at 20% depth of discharge. In a sense, the amount of energy it reduces, but it can operate longer. And for example, a 120 ampere hour battery rated for 10-hour discharge, C10, will be fully discharged in 10 hours. And it will supply a uniform 10 ampere current. If discharged at a higher rate, then the battery capacity is reduced and it will be less than 100 ampere hour. Okay, in the sense, so 12 ampere current you get for 10 hours. You can multiply it by 10. So 12 ampere each hour, and it operates for 10 hours. So that becomes 120 ampere hour battery. And then we have an inverter. These inverters are basically what help convert the electricity generated at the solar cell into, how do you say, the electricity that can be used at home, which is the alternating current. Because what we get from the solar cell is direct current. So it has to be converted into alternating current, which can be used at home. So then that is why we need an inverter, even if we get a solar cell, in the sense that solar panel. These are some components that are basic requirement for the operation of the solar cell. And then we have a charge controller. So basically what this component does is to reduce the amount of excess voltage that can be generated from the solar cell. Sometimes you cannot determine as to how much energy the solar cell can give out. So these charge controllers, they give you a uniform input voltage to the battery so that none of the components get affected. And so we've covered many subsystems now. So we have the solar photovoltaic panels, then we have the batteries, then the power converters, and then the electric loads, which are like the lights, the fans, etc. And the last component is called the balance of system. So what is the balance of system is that you need mounting structures for the panel, in the sense they have to be kept at an incline. And then there is labor. Then there are fuses and switches which need to be present. Then there is wiring, and then you also need an energy meter. So these are all the components that go into the working of a solar cell, especially for buildings. I have talked about buildings before this time because it is the most widely accepted form of solar energy. In the sense, you don't see Lightyear 1 car already everywhere, but you do see solar panels on top of buildings. So I thought that I would better explain how you have the different type of components for solar power in buildings. And I think I've come to the end of my talk. Thanks a lot for listening. And if you have any questions, please let us know.
Thank you, Adhish. Riani, do we have questions?
I think we have one question which was on the chat box. I don't know who it's addressed to, but I think anyone who would know can answer this. And it's from Rajesh. This is actually from a college which is called Namchi College, and they have posed this question. It is, let me just find it. Yeah. So his question is, he's saying, we all know that methane is more polluting. Is there anything related to carbonizing methane?
I think biogas plants make use of methane. So that is the most appropriate use for biogas plants. But apart from that, I don't see other uses for methane. Maybe the other speakers.
So, I guess, well, in UK, we use a lot of natural gas, mainly methane. So in order to replace the use of them, well, people have probably two alternative solutions. One is electrify your energy system. In order, for example, instead of burning natural gas, you use electric cooker. Another one is using green hydrogen to replace diesel. That's another way, but it's more long-term solution. So far, that is two options I can see so far. Yeah.
Do we have any other questions in the audience? If we do, just like you can raise your hands and we can try to address it in the next few minutes. Ritesh, your hand is up again. Do you have another question? Or is that?
There is a question in Q&A. So where Rajesh is asking, can we have a financial benefit if we use off-grid power? So can I answer this? Yeah, so I'll share my views and then other panelists can add their views on this. So with the off-grid power, the issue is we need a battery. For off-grid power cannot work without battery because this wind and solar. Wind is a very large scale generation, and solar can be have in a rooftop or small village or this kind of off-grid situations, but it is not very farm. So for solar to operate, we always need a reference voltage to farm it up. So for that, we need a battery in our off-grid power system. And as you all know that even though the solar panels, they have a lifespan of 25 years, but the batteries don't have. So it varies depending on the type of battery used. It can vary from 5 to 10 years. And as Adish was telling in his very nice presentation, that it all depends on the depth of discharge also. That how much lifespan you will get from the battery, how many times, how frequent you have to replace. And replacing means cost. So that way, an off-grid solar plant is much more expensive compared to a grid-connected one. However, they are useful when we talk about Ladakh and those kind of places which are very remote and grid cannot reach there. So we have to do a cost-benefit analysis, whether we should take the grid that far. Do we have that many consumers there for taking the grid there, or how long we are taking over what part, Himalayas or where we are going? Or we should have a battery and try to do in an off-grid way. So we have to strike a balance between these two. And of course, there are issues of maintenance and all other things with off-grid that raises again a social question. Like the people who are in small hamlets, whether you should make them suffer from repairing their own solar plant, and while the people which we are in the city and all, we get a grid connected supply. So what do you do? That's another question which can be asked. So that's my take on this issue of cost, benefit, and all that in off-grid power. Please, Adish and Barton, please add your views also.
No, I think you have covered everything. That's nice. Thanks a lot.
I think there's probably one thing I want to add is if renewable energy is competitive or cost effective, also depends on the cost of the other things, because the war in Ukraine now it really increased the cost of natural gas. So in the past 1 year in Europe, the cost of renewable energy is really well, it's not really lower, but it's cheaper than fossil fuel. So that can make renewable energy more economic, fixable. Another thing is in Europe, they're going to have a carbon tax. So it means when you use fossil fuel, the cost will be even higher. So that can make, using renewable make more sense in the future. Yeah, that's my view.
Is there any more questions from the audience? I think take one last if there is, otherwise, if not, I think that was a really good session. Should we wait for another minute and see if there is a question? And then maybe- I think that's about it. I think there's no more questions coming up, I think, yeah.
Yeah. So if there is no other question, I would like to close the session. So on behalf of Smriti and Chair Divecha Center for Climate Change, I would like to thank all the panelists and participants, all the schools and people from IISc who have joined here. And thank you so much for coming. Hope you like the session. And if you have any question, please feel free to reach us. And thank you. Thank you again. Bye.
Thank you so much, everyone. Thank you.
Thank you.
Have a good one. Yes.